In this video, I'm going to demonstrate how to perform a binary logistic regression analysis using Intellectus. As you can see here, we have a data set, and however you enter in your data set, you could enter in the data in by hand or import into Intellectus using an Excel file or an SPSS data file. It'll accept many different types of versions of files. So what we're going to attempt to do here is we're going to try and predict a dichotomous outcome. We're going to work with the variable called group, and so we're going to consider this to be whether or not someone passed or failed an exam. So group A are the people that passed the exam, and group B would be the people that failed the exam. And so what we want to try and do is find some independent variables that could then predict someone's membership in this group of either pass or fail. And so we're going to attempt to see if there are a number of variables that can predict whether or not someone will pass an exam. So that group membership, that's our dependent variable. And then we're going to have three independent variables that we're going to use to try and predict membership in that group. And so the three we're going to use are reading number 3, score on a reading assessment. We're going to use sex, but in this case, this is also binary, male or female. And we're going to use math scores as well to try and predict whether or not someone passes this exam. So one of the assumptions we have to make is that there is not multicollinearity among our independent variables, and I'll demonstrate how to assess that in the output. Our independent variables do not need to be normally distributed. They can be skewed, and they can be a combination of nominal, ordinal, and numeric. They don't have to be one or the other. They can be a combination of those three. But the outcome has to be dichotomous. It has to have only two possible outcomes. Okay, so once we've kind of have our data arranged, our next step is to actually run the analysis. So we're going to go to the analysis menu. We're going to find the regression menu, and then we're going to find binary logistic regression. And so what Intellectus does is when you hover over a choice, it'll give you a description of what that analysis entails as far as the type of data and the levels within that data that are appropriate. So you can see the description here. If we have one or more scale, ordinal, or nominal level independent variables, and we're using them to predict a nominal level dependent variable with two levels, dichotomous variable. Okay, so we're going to choose a binary logistic regression. And our menu option here is pretty simple. So the first thing we want to do is identify our dependent variable. So we click on the Add button. And then you'll see a drop-down menu of our dependent variable choices. And you'll notice that the only choices it will give you are the variables that are dichotomous nominal scale variables. So in this case, the one we're going to work with is group. And one thing it's going to ask you for is the reference category. And this is typically the option within our outcome that we want to compare against. So we're interested in knowing what can predict if someone's going to pass an exam. And so failing the exam, or group B, would be our reference category. Sometimes we might want to know the opposite types of things. We want to know if we can predict if someone's going to fail an exam. And in that case, group A would become our reference category. So it's somewhat arbitrary as far as how you want to do that. But very often we use the null or the absence of something we're interested in is our reference category. So that might be doesn't have a disease, or fails a test, or doesn't have a characteristic. Those are often treated as our reference category, but it doesn't have to be. But in this case, that's what we want it to be. We want failing the exam as our reference because we want to understand what helps us predict someone passing an exam. So once we've entered that bit of information in, we click confirm. Okay, and we next need to add in our independent variables. So we click our add modify button, and then we just check off the variables we're interested in. So we're interested in this case, reading number 3, sex, and math scores. Okay, that's all we need to do at this point. Then we click confirm, and we don't need to mess with any of the other options. Once we've got our data entered, we go ahead and click the calculate button. Okay, and we're going to work from the raw output. So up here at the top where it says output format, you have the option of an interpreted output in which Intellectus actually interprets things for you and writes it out in a narrative, which can be helpful for language. This is not something you should copy and paste into a results section because it's not always completely appropriate as it's written. So we really want to be careful there. But it does give you some sense of what language to use when interpreting our output. But I want you to be comfortable with the raw output, so we're going to look at that. Pretty simple, pretty straightforward. So the first thing we want to do is look at that multicollinearity assumption that we talked about. And again, that's a situation where we have independent variables that are highly related to one another, which would then indicate there's some redundancy among those independent variables that have high multicollinearity. We don't want redundancy. We want each variable to kind of give us a different aspect of the outcome. And so we want to eliminate multicollinearity if it's there. So the first thing we can do is look at something called the variance inflation factors. And what these do is these calculate, it gives us kind of an overall sense of whether or not those multicollinearity present among our different variables. And so if we have VIF scores above 5, that's kind of borderline concerning. And if we have a VIF value that's greater than 10, that indicates there is multicollinearity present. And so then we need to go back and do either Pearson or Spearman correlations to find out exactly which variables have these multicollinearities. And then we likely would need to eliminate one of them so we can eliminate the multicollinearity. But as you look in this table here, you can see the VIF values are all less than 5. So that indicates that there is not multicollinearity present among these 3 independent variables. So that's a good thing. That's what we want to see. Okay, the next thing we can look at is down here at the bottom where it says model fit statistics. And this tells us whether or not our model is a statistically significant predictor. In other words, can it predict membership in group A or group B above and beyond chance? If we were to flip a coin to say you'll be in group A or group B, that's chance, 50-50 possibility of being correct. But the model fit statistics will tell us if our model is statistically significant in its prediction. In other words, it's better than chance. And so what we get in this is a chi-square value, and we can see this is a fairly high chi-square value. And then we can see our p-value here. And what you'll see here is when we have a really small p-value, which in this case we do, the p-value is written out in scientific notations. So that indicates that there is a number of zeros in front of 252. So our p-value is something like 0.000000 2.52. In other words, it is much less than 0.05. So we can say that our model is statistically significant in the sense that it is better than chance. Another thing we can look at is this Mcfadden R² value. And this also gives us an idea of the model fit, how well the model fits reality. And any value above 0.2 is considered to be clinically significant. So we can see here we have a value of 0.64. So that indicates that we have excellent fit in that the model is most likely clinically or practically significant. So those are 2 good things. That means our model is, number 1, better than chance as far as predicting the outcome. And then it's also practically or clinically significant. In other words, the ability to predict is going to have importance, practically speaking. Okay, the last thing we can look at is look at our individual independent variables and their contribution to the model and their ability to help us predict that particular outcome. So as we look at, we can ignore the intercept line, and we're going to look at the 3 rows that indicate our 3 independent variables that we chose. And we can see we have a beta coefficient that's reported. But what we're really most interested in is looking at the p-value associated with each outcome, or each predictor, excuse me, as well as the odds ratio, and then the confidence intervals for that odds ratio. So the first thing we can look at is looking at reading 3. We can see its p-value is 0.75. It's greater than 0.05, so that indicates that reading 3 did not have a significant effect on the odds of observing category A or group A being present. So that indicates that that's probably not, it's not contributing to our model in any meaningful way. And you can see the odds ratio is 1.049. So there's no increase in odds in predicting membership in category A with the reading 3 variable. If we look at sex, we can see the p-value there is 0.74. So it is also a non-significant predictor of being in group A. And we can see the odds ratio is a little bit higher, 1.2, but that's not really significant because and if we look at our confidence intervals, we can see for both of these variables, reading 3 and sex 2, the confidence interval for the odds ratio crosses 1, which is the null hypothesis. So that's why we see a non-significant result for these two variables. So if looking at the confidence intervals, you remember the confidence interval tells us what is likely to be the case in the population, that reading 3 and sex 2 might actually have the opposite effect in the odds ratio that we're looking for. It might actually be worse or make the prediction worse than better. So that's why these two variables are non-significant, and then we've got these fairly small odds ratios. As we look at math scores, however, we can see that the p-value is obviously less than 0.05. And so math scores are a significant predictor or a significant contributor to our model. And we can see the odds ratio here is 2.0. So that indicates that for any 1 unit increase in math scores, the odds of observing the group A category of group, in other words, passing the exam, would increase by around 100% or a little over 100%. So that's what's meant by an odds of 2 times greater to predict that. So that shows that the math score was the strongest predictor in this model in being able to predict whether or not someone's going to pass or fail an exam. And as we look at the odds, the confidence interval for that particular odds ratio for math scores, we can see that there's a fairly wide range here, 1.3 to 3.1, but that lower value still does not cross 0 or does not cross 1. So again, that indicates that we have a significant predictor, and one that will likely be a good predictor in the population as well as what we're seeing in our sample here. So to summarize, we attempted to do a binary logistic regression to predict someone passing a particular exam, and we used 3 independent variables: a reading assessment score, sex, and then a math assessment score to predict whether or not you were going to pass or fail another exam. And we found that 2 of the 3 variables were not significant contributors to that model, but the third, math scores, was, and it was significant at the 0.05 level, and the odds ratio for predicting the group A or the passing the exam was 2.0, and the odds ratio confidence interval does not cross 1. The overall model fit is statistically significant, and our Mcfadden R squared, which is again an indicator of clinical or practical significance, was 0.64, which is greater than kind of that threshold of 0.2, which indicates we have a practically significant model. Now, some of you are probably thinking, well, reading 3 and sex were not significant contributors, so do they need to stay in the model? You could argue no, that you could take them out and just have a model using math scores to predict someone's passing or failing another exam. Or there might be some other variables we want to include in a model, but that's part of the trial and error process that we have in any regression that we develop, regression model that we develop. But this is an example of how to develop that kind of regression model when we have a dichotomous outcome as opposed to a numeric outcome. So again, hopefully you found this to be useful, and good luck using this in your own research. Take care.